This video is sponsored by Squarespace. The first full-color images captured by the brand new Euclid Space Telescope have been made public, and they did not disappoint. Never before has a telescope been able to create such razor-sharp astronomical images across such a large patch of the sky and look so far into the distant universe. These inaugural images showcase Euclid's extraordinary capability to create the most comprehensive 3D map of the universe yet. But what's so special about the Euclid Space Telescope? How is it different from the $10 billion James Webb Space Telescope? And what's so special about these 5 images captured by Euclid from the edge of darkness? Let's have a look at them one by one. First up is this incredible view of the Perseus galaxy cluster. The Perseus cluster is one of the most massive galaxy clusters, located about 240 million light-years away. Euclid's view comprises about 1,000 galaxies belonging to this cluster. But what's even more remarkable is that there are over 100,000 additional galaxies in the background. Thanks to Euclid's groundbreaking imaging capabilities, most of these galaxies are being photographed for the first time. Also, light from some of these far-flung galaxies has traveled for 10 billion years to reach us. For an astronomer, such an image is a treasure trove that can reveal many secrets of the cosmos. Firstly, the existence of a galaxy cluster like Perseus, housing thousands of galaxies bound together by gravity, is only possible if dark matter plays a crucial role in holding it together. By capturing galaxy clusters like Perseus and studying the distribution and shapes of galaxies in them, we can understand the role of dark matter in the universe's evolution. Among the other galaxies in the cluster, the tiny ones that were not imaged previously are of utmost interest to astronomers. The tiny faint galaxies are dwarf galaxies, which according to the theoretical prediction must be large in number but are strangely scarce. Euclid's high-quality images can lead us to the solution to the dwarf galaxy problem. In addition, the shapes of these galaxies in the background and within the cluster appeal to astronomers. The weak lensing effect caused by dark matter in and around the cluster causes the shape distortions. Weak lensing analysis helps in understanding the distribution of dark matter. At least 50,000 galaxies captured in this image can be used to map dark matter distribution by studying weak lensing. Now let's take a closer look at the remarkable spiral galaxy IC342, situated approximately 11 million light-years away from Earth. It is located behind the Milky Way band in the sky. Our own galaxy's active, gas-rich, and dusty disk obstructs our direct view of this stunning spiral. However, thanks to the near-infrared instrument on board Euclid, we can see through the dust and examine the light emitted by the stars that dominate the galaxy's mass and brightness. Notably, this is not the first time IC342 has been captured on camera. In 2017, NASA's Hubble Space Telescope managed to overcome the challenges and image this galaxy using its Wide-Field Camera 3. Yet, what sets this image apart is Euclid's ability to zoom in on individual stars and star clusters and extract details about their formation process and evolutionary history throughout the galaxy's lifetime. This level of detail was simply not achievable with previous Hubble Space Telescope images. Since IC342 is a spiral galaxy, studying it is equivalent to studying galaxies like our own. Before we talk about the rest of the images, let me introduce you to the sponsor of this video, Squarespace. If you're someone who has no coding experience or software knowledge but still want to establish an online presence, like building a website or an e-commerce store, Squarespace has got your back. With Squarespace, you can easily create a stunning website, showcase your work, and connect with your audience without the need of hiring a developer. Squarespace also offers powerful blogging tools for sharing ideas, scheduling content, and integrating with third-party tools through Squarespace extensions. Plus, with Squarespace email campaigns, you can effortlessly gather email subscribers, promote sales, and offer discount codes. They even provide built-in analytics to measure the impact of your email campaigns. So if you want to give it a try, you can visit squarespace.com/the secrets of the universe. And if you like it, you can get a 10% discount off your very first purchase by clicking the link in the description. Now let's turn our attention to the most stunning image captured by Euclid, the Horsehead Nebula. It is the closest large star-forming region to Earth, located approximately 1,375 light-years away. Its distinctive shape, reminiscent of a horse's head, has earned its unique nickname. The Horsehead Nebula is a popular astrophotography target. However, astronomers are so interested in it because the radiation from the luminous star Sigma Orionis, situated just above the nebula and outside Euclid's range of vision in this image, is causing star formation under special conditions. The ultraviolet radiation from Sigma Orionis lights up the nebulous clouds behind the Horsehead, creating a striking contrast with the Horsehead's dense, dark clouds, which block out the illumination. This interplay of light and shadow lends the Horsehead Nebula its captivating appearance. Sigma Orionis is part of an open star cluster with over 100 other stars. While the Gaia mission successfully identified many additional cluster members, not all have been captured in images. Furthermore, this image has led to the discovery of new candidate stars, brown dwarfs, and planetary mass objects within the region. With Euclid's advanced capabilities, scientists aim to get a complete picture of the open cluster. The next top-notch image is of the irregular galaxy NGC 6822, located just 1.6 million light-years from us. It belongs to the same galaxy cluster as the Milky Way, the Local Group. While various telescopes have observed NGC 6822 in the past, Euclid made history by capturing the first high-resolution image of this galaxy and its surroundings within just 1 hour of exposure time. What sets NGC 6822 apart is its low abundance of elements other than hydrogen and helium. A galaxy's metallicity, or the presence of heavier elements, tends to increase with its evolution. This progression occurs as the first-generation stars complete their life cycles, enriching the galaxy's chemical composition. So studying metal-poor galaxies like NGC 6822 offers valuable insights into the early universe's galactic evolution. The last of the 5 images is of the second closest globular cluster to Earth, NGC 6397. Globular clusters are some of the oldest structures in the universe. They contain a treasure trove of information about the formation and evolution of host galaxies. The cores of globular clusters are bright because of the high concentration of stars. These stars overshine the low-mass, faint stars on the outskirts, which are located there most likely because of previous interactions with the galaxy. Since the faint stars contain a history of interactions with the galaxy, it is vital to measure their light. While Hubble requires extended observation time to image these fainter stars, and Gaia tracks the trajectories of globular clusters without revealing much about the faint stars, Euclid's wide field of view allows it to capture the entire globular cluster within just 1 hour of observation. The presence or absence of faint stars at the outer limits of globular clusters holds significant implications for our understanding of dark matter distribution. If there are no tidal tails or faint stars, it could suggest that a dark matter halo is shielding the outer stars from escaping during interactions. However, this scenario is considered highly improbable, as dark matter halos are more commonly associated with larger structures, such as dwarf galaxies and galaxies, rather than compact globular clusters. The Euclid spacecraft has been designed and developed by the European Space Agency, with contributions from NASA. Its primary mission is to create a 3-dimensional map of the universe, where time serves as the 3rd dimension. This ambitious endeavor involves the observation of billions of galaxies, reaching as far as 10 billion light-years away, ultimately creating a comprehensive chart that illustrates the cosmic evolution throughout the universe's lifetime. Euclid aims to cover 1/3 of the sky to unveil the dark universe. The 2 mysterious entities that dominate the universe are dark energy and dark matter. According to the current cosmological model, together they make up 95% of the observable universe. By observing the evolving universe, Euclid will reveal the structure, formation, and expansion of the universe. Through this, astronomers intend to understand the true nature of dark energy, dark matter, and gravity. There are 4 important questions that Euclid will try to answer. What is the true nature of dark matter and dark energy? What is the mechanism of structure formation and history of the cosmic web? Is the Hubble tension, the apparent inconsistency in the rate of the universe's expansion, a genuine phenomenon? And finally, is there any flaw in our understanding of gravity? It's important to note that Euclid differs in its scientific focus from other renowned space telescopes, such as the James Webb Space Telescope. Webb primarily seeks to explore the early universe, whereas Euclid aims to investigate dark energy and dark matter. Also, while Webb was designed to focus on a smaller fraction of the sky with the highest resolution possible, Euclid is designed to optimize and cover large areas of the sky much faster. Finally, Webb zooms in and observes individual objects in the early universe, whereas Euclid takes wide images of the sky, covering a large fraction of it. Similar to Webb's near-infrared camera, or NIRCam, Euclid will measure light at near-infrared wavelengths, but its observing area of the sky is 100 times greater than NIRCam. Consequently, the wide field of view observations of Euclid will provide potential targets for JWST and other observatories. These images from the Euclid Space Telescope not only demonstrate its technological prowess, but also mark a significant step forward in our understanding of the universe, its composition, and its evolution. Recently, the James Webb Space Telescope observed Jupiter's moon Europa for 10 hours and found a potential sign of life originating from the ocean beneath its surface. If you missed this episode, be sure to catch up on the exciting discovery.